All right, problem 1. Is Paul tall? I'm going to say yes, but let's actually calculate it. So according to the National Center for Health Statistics, the distribution of heights for 15-year-old males is a mean of 170 centimeters and a standard deviation of 7.5 centimeters. Paul is 15 years old and 179 meters tall. So this has a mean. Well, first I'll write the mean. Mu is 170. Sigma for standard deviation is 7.5. Paul is 15 years old and his value, his height is, we'll make it x, which is 179. So in part A, we got to find the z-score corresponding to Paul's height and explain what this value means. All right, remember the z-score is a value that tells you essentially how far it is from the mean. By how far, we're giving you a number that is actually the number of standard deviations from the mean. So the z-score is equal to the individual value or the data value, x, minus the mean over the standard deviation. So in this case, z would be 179 minus 170 over 7.5. We'll get 9 over 7.5. Oh, bang, 1.2. 1.2. That was weird. Okay, so then we can just say that Paul is 1.2 standard deviations above the average male height for his age. Part B. Paul's height puts him at the 85th percentile among 15-year-old males. Explain what this means to someone who knows no statistics. Man, that's a boring life. But it just means that he's taller than 85% of 15-year-old males. So the percentile, remember, is like a ranking. The closer you are to 100, or the higher the percentile, the I guess the more superior you are to your peers. So if you're at the 100%, well, you can't really be at the 100 percentile, but so they'll usually cap it at 99. I mean, I guess you can, but no, you can't. You can't be taller than yourself. But that's why they usually will go to 99. So 85th percentile, he's taller than 85% of all the males his height. I mean, he's taller than 85% of the males of his age. Okay. Problem B, Miss Kazi asked, what's with these names? Miss Kazi asked her students how much time they spent using the computer during the previous week. The following figure, right here. Over there. There we go. Following figure shows a cumulative relative frequency graph of her students' responses. For what percentile does a student who used her computer for 7 hours last week fall? Okay, so since it's not drawn to where you can see the grid lines, let me bust out my ruler so we can get some accurate measurements here. So then 7 hours last week, 7 will be about right here. So what we do is we draw a vertical line. It does this sort of thing, and we want to see where it intersects the graph. And from there we draw a horizontal. Yeah. So then this will be about like 56 percentile. Because it's a little more, but again, this is approximation, so we'll say about 56 percentile. Estimate the interquartile range from this graph. All right, interquartile, remember, is the 25th percentile to the 75th percentile. So 25th percentile is right in here. 75th is in here. So we draw two horizontal lines, see where they intersect the graph, and then drop two verticals. So kind of like the opposites. Or just going backwards, I guess. Like being percent. What's this stuff? Who knows? So right about 3, and I guess you can't expect it to be, exact. So I would say from about 3 to 11, or you could say 2 to 11. That sort of thing. The answer key is 8.5. So yes, I got it. I'm professional. So 2.5 to 8, or 2.5 to 11. But on a test, they'll be much more clear. It won't be like this old school graph. All right, problem 3. The Aussie. That's for Australia. I went there once. It was cool, and hopefully I'll go back again. A group of Australian students were asked to estimate the width of their classroom in feet. Use a dot plot and summary statistics below to answer the following questions. In your textbook, this is printed better, but this is a black and white sheet. Here's the data. And the means, standard deviation, all this is given in feet. But it's saying, let's suppose we converted each student's guess from feet to meters. Now, how would this affect the shape of the distribution? Find the mean, median, standard deviation, and IQR for the transform data. All right, so like the shape ain't gonna change because the shape doesn't depend on the scale. The shape is a shape, you know? Like if I have a square, if I zoom in, it's still a shape. I mean, it's still a square. If I zoom out, it's still a square, it just appears smaller. So what I mean, like maybe from this angle, it's 1 centimeter. But when you zoom in, it's like, it's like a foot or something. But the shape is not going to change. That's just to give you like an intuitive. Now the mean, yeah, it's going to change by the multiple. But since we're going from the smaller to the bigger one, we're going to divide by 3.28. So the mean, the new mean will be the old mean divided by 3.28. So it would be 43.7 divided by 3.28. And we'll get about 13.32. Now, whoops. We got to also find the median and standard deviation and IQR. Median, same thing. You multiply it or you divide it by 3.28. So this is the mean. Median. 42 divided by 3.28. Bang. 12.8. The standard deviation, divide, and IQR, you all divide all of these. Standard deviation, 12.5 divided by 3.28. 12.5 divided by 3.73 meters. And then the IQR. The IQR doesn't give us it, but we can find it. 35 to 48 is 12 and 12 and a half. So we do the new IQR is going to be 12 and a half divided by 3.28. So about 3.82. Apologies, I usually don't cram my answers in here, but you know, desperate times call for desperate measures. You gotta do the math. All right, problem 3. Problem 4. What the mean means. Ha 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 ha. Clever. The figure below is a density curve. Really? That doesn't look. Well, I guess it is. Looks like a slide or a mountain. Mark the approximate location of the median. Explain your choice of location. So median's geometrically it's the equal areas point. So find the 50 percentile. Or 50% of the area. I would actually stay over here as the median. No. Well, I guess between those two actually. Median, that's the new median. Because equal areas, 50-50. The mean. The mean will be more towards the tail, so maybe we could say the mean is over here. Because the mean is sensitive to outliers, meaning that larger extreme values, the mean is going to be pulled in that direction. And we call this sensitivity to outliers. Horse pregnancies. Bigger animals tend to carry their young longer before birth. The length of horse pregnancies from conception to birth varies according to roughly normal distribution, with mean 336 days and standard deviation 3 days. Use the 6895-997 rule to answer the following questions. Almost 99.7% of all horse pregnancies fall in what length or what interval? Okay, so remember how the normal curve works. It's a bell-shaped curve. It's symmetrical, centered at the mean or 0. At z-scores, it's 0. One standard deviation. It usually goes 1, 2, and 3 in terms of z-scores or standard deviation values. Make sure you know this by the end of this chapter. This will haunt you if you don't know it for the rest of your stats life. Now, the 997% is referring to 3 standard deviations away. So from here to here, that's 99.7% about approximately of the entire area. So we have to find out what these values are. Using this data, the mean is 336. So the middle here would be 336. We add 3 times the standard deviation. Standard deviation is 3. So, see, this would be then 339, 342, and then this would be 345. Whoops. So 345 to the right, all the way to the left would be -9, so 327. So about the interval is 327 to 345 for about 99.7% of horse pregnancy lengths. Days. Almost a year. Alright. Oh, what percent of horse pregnancies are larger? Whoa. What percent of horse pregnancies are longer than 339 days? Larger. Well, I guess, actually, never mind. So we find basically the area to the right of 339. Ah, I see. So we want to find this area. So remember 68%, you can use logic. 68% is this entire area from here to here. Let me use a different color pen. 68% is this whole thing. But since it's symmetrical, we know then that 34% will be over here. This red region. And since it's symmetrical, that means that the remaining part over here has to be 16% because it has to be adding to 50. So the answer will be 16%. All right, using table A or technology, I got you. Find each of the following standard for a standard normal distribution. In each case, sketch a standard normal curve and then shade the area of interest. All right, let's first sketch it. So we want to find the area from negative 2.25. So remember the 0 is the center, normal mean of 0, standard deviation of 1. So negative 2.25 standard deviations to the left, and about 1.77 to the right. So we're finding this area. So in your calculator, there's this cool function under distribution. First you gotta turn it on. There we go. Distribution. Then you go to normal CDF. In this old school calculator, you have to have the syntax memorized. And this will be the lower bound, or negative 2.25, comma, upper bound, 1.77. And this is going to be followed by the mean and standard deviation. You don't have to actually type it if you're talking about the standard normal curve, where the mean is 1 and standard deviation is 0, but just to make sure you get it. So lower bound, upper bound, mean, standard deviation, and what did I do? Oh, I did it wrong. I flipped those 1 and 0s. I said it correctly, but I flipped them. Negative 2.25, comma, 1.77, comma, 0, comma, 1. But bang, about 95%. Now, the number such that 35% of all observations are greater than z. So drawing a little sketch here. So we want to find the z-score where 0.35 is to the left. Or sorry, 0.35 is to the right. So 0.35 is to the right. That means that 0.65 is to the left. And there's actually another function you can use under distribution again, or vars. Inverse norm. Here you go from the area to the z-score. So the syntax here is type the negative, or type the left area. So 0.65. And that's really it. You can also enter the mean and standard deviation. But again, by default, it's always gonna do the standard normal distribution, where the mean is 0 and standard deviation is 1 if you don't type anything. And we get about 39%. Or no, it's not 39%. Z is 39. Or Z is 0.39. All right. Water break. Or a couple more. All right, low birth weight babies. Researchers in Norway analyzed data on the birth weights of 400,000 newborns. That's a lot of babies. That's like an army of babies. Hopefully they didn't piss them off. Over a 6-year period, the distribution of 400,000, geez. The distribution of birth weights is normal with a mean of 36.68 grams and standard deviation 511. Babies that weigh less than 2,500 grams at birth are classified as low birth weight. What percent of babies will be identified as low birth weights? Okay. So, normal distribution, mean of 3,668, standard deviation of 511. So below 2,500, 2,500 is way low. Because if it's going to be about like 2 standard deviations, because 1 standard deviation is 5. This is about more than 1,000 grams less than the mean. So you want to find the area over here. And then you can just use the normal, or you can use the normal CDF function in your calculator, because you're just basically looking from the area to the, if you were to go all the way to the left infinitely, you want to type a very large negative number, so like negative a billion, negative 10,000. So then this will be the negative a billion will be your left bound, your right bound or upper bound will be 2,500. So then we go to distribution, normal CDF. Lower bound is type a very large negative number. Upper bound 2,500. Now here, to save yourself some time and to calculate, to make any extra calculations for the z-scores, you can just rewrite this and have it, or not rewrite it, but you can just enter the mean and standard deviation of this distribution. So the mean will be 3,668, right? And comma 511 for the standard deviation. Yeah, like 1.1% babies. That was a fat baby. Oh, I'll say chubby baby. So that was good. I was probably on the other 1.1%. Find the quartiles of the birth weight distribution. Show your work. Okay, so 25 percentiles. Okay, so then we just look for the, let's go over here. What value is going to be 0.25 to the left and the other one 0.25 to the right? This is centered at 3,668, so we want to find this value. What is it? We call, I'm going to call that Z1. This will be Z2. Now, I mean, all you got to do really is do inverse norm, because we got the mean and the standard deviation is still 511. So we're going to go back to our distribution. Inverse norm, area to the left is 0.25. Comma the mean 3,668, comma standard deviation 511, and bang, 3,323. That makes sense. 3,323.335. A lot of threes here. There's all threes for days. And then you do the opposite for that. Or you can find the difference and add that to here. So like we find how far away this is from 3,668. So 3,668 minus 3,323.335. So about 345 grams. So we just add this number to 3,668 and that'll give us the other side because they're symmetrical. Yeah, so Z2 will be 4,012.665-ish. So these are going to be your first course, be Q1 to Q3. All right, let's go through one or two more. Ketchup one. A fast food restaurant has just installed a new automatic ketchup dispenser. Hold up a second. In preparation for his burgers. The amount of ketchup dispersed by the machine follows a normal distribution with a mean 1.05 and standard deviation 0.008. So normal with the mean. Their goal is to put between 1 and 1.2 ounces of ketchup on each burger. It's kind of a lot, isn't it? I'm not a big fan of ketchup. I'll eat it if I have to, but you know. So what's the area? So essentially, what's the area between 1 and 1.2 in this distribution? So draw my normal curve. I spaced out there for a second. Just use your calculator again. Normal CDF, lower bound is 1 point, or just 1. Upper is 1.2. Mean is 1.05. Standard deviation is 0.08. We got about 70.3%. All right. So C minus. All right, part B. Suppose the manager adjusts the machine's settings so that the mean amount of ketchup dispensed is 1.1 ounces. How much does the machine standard deviation have to be reduced to ensure that at least 99% of the restaurant's burgers have between 1 and 1.2 ounces of ketchup on them? Well, you see what's going on here is some calculations that we gotta do. Okay, so let's do this one like this. So we got a mean of 1.1, normal distribution. 1.1 will be in the middle. They want 1 ounce and 1.2, so it's nice. At least it's 1 ounce less and greater than the mean. Now we're told the mean is 1.1, so we're gonna find oh yes, and we're also given the area here, 0.99. So what we want to do is find the z-score where there's going to be an area of 0.05, so of 0.5%, 0.005 I guess, to the left. Then once we find that z value, we then can solve this equation where we have z equals, again, x minus the mean over the standard deviation. Z is going to be, our x is going to be 1. The mean is 1.1. And we still have to find the standard deviation. But once we get the z, we can find the standard deviation. So we just go inverse norm. 0.005. 0.5%. And that'll give us a z-score about negative 2.58, which makes sense. So now we just solve this. So doing the math, negative 2.58 equals 1 minus 1.1, so negative 0.1 over sigma. So what we can do is multiply that by negative 2.58, and then undo it by dividing. Because if we multiply this by sigma, we get 2.58 sigma. but then we can just go back and divide. So we just get the sigma on the left, and we divide the right by negative 2.58, which is a small ass standard deviation, 0.1 divided by 2.58. Well, not that small, I guess. 0.0387. So 0.0387. It's going to be the new standard deviation. Yeah. All right, let's go through one more. The grading managers. Many companies grade on a bell curve to compare the performance of their managers and professional workers. This forces the use of some low performance ratings because we don't want them all getting A's. Ford Motor Companies. That's their process. For a time, they assign 10% A's, 80% B's, and 10% C's for 18,000 managers. Damn. It's a big company. Now, if these are normally distributed, it's going to have a beautiful bell curve like this. 10% is to the right of an A, 0.10. 80% are B's, so 0.8 is, or the B's are all up in here, are in the middle. And then, again, on the left, 10% are the C's. So you got your B's, got your A's, got your C's. So this year, managers with scores less than 25 received C's, so 25. And those with scores above 475 received A's. So what are the mean and standard deviation of the scores? So a good thing we got a picture, because that means the mean is going to be the middle of 25 and 475. And that'll be 250, right? Because, yeah. Add them, 500, divide by 2 is 250. So this is the mean. And then to find a standard deviation, we just have to pick an arbitrary, just set up a z value, or z equation. So z, remember z equals x minus mu over the standard deviation. This can just be then, let's make the z 25. No, let's make, what did I have it before? Wait a minute, is it? Oh yeah, no, okay, never, we're good. Okay, oh yeah, duh. So we got to solve for z. Find what value has 10% to the left, and back to our inverse norm. 0.1. You get a z of negative 1.28. So we set up our equation of negative 1.28 equals 25 for x minus 250 for the mean over sigma. Solving this, we get sigma equals negative 225 over negative 1.28. $175.78. Wait, what? Is that really it? That makes sense. Yeah, actually it does. It's because the values are so spread out among the centers. Oh, that's it? No, that's easy. I mean, not a problem. We're done. The other ones are just some tedious grabs, I'll do them in another video in case some of you want them, but you're not really tested on those. Also, they're just tedious. Alright, so if you can do all that, you're gonna ace this test. If you can do it. Make sure you can do it, practice it. So yeah. Hope that helps. If it does, make sure you hit that like or subscribe and leave me some feedback so I can always get better. And I appreciate you guys watching, and I'll see you guys next time.